Welcome to the Deep Dive. Today, we're going beyond the runway and taking a close look at something we see on every flight but rarely think about in detail: aircraft landing gear systems.
Yeah, absolutely.
You sent us a really in-depth chapter on this topic, and our mission today is, well, to uncover the most fascinating and crucial aspects for you.
Exactly. It's much more than just how planes roll on the ground, isn't it?
Mm-hmm.
Aircraft landing gear is really a testament to some ingenious engineering. It has to adapt to a huge range of environments. I mean, think about it. Beyond the familiar wheeled systems, you've got helicopters using sleek skids.
Right.
Bush planes, fitted with robust skis for snow and ice, and seaplanes using pontoons for landing on water.
That figure, 13-to-1, really shows that variety.
It does. That adaptability is absolutely key to the versatility of aviation.
Totally. And it's not just about what touches down, but the fundamental layouts, too. The chapter breaks down three basic arrangements: tailwheel, or conventional gear, tandem, and tricycle gear. And these different setups aren't just cosmetic, they have a big impact on handling.
Precisely. And at their core, all these different systems share a couple of vital functions.
Yeah.
First, obviously, they have to bear the entire weight of the aircraft when it's on the ground.
Makes sense.
And just as critically, they've got to absorb the, well, often substantial impact forces during landing.
Right, that controlled transition from flying to stopped. And the chapter also mentions a basic classification based on movement: fixed or retractable.
Yep.
It hints at that trade-off, where tucking the wheels away reduces drag, boosts performance.
But adds complexity and weight.
Yeah.
The classic engineering compromise.
Exactly. Okay, let's dive into those different arrangements then. Starting with tailwheel or conventional gear. Why do they call it conventional?
Good question. It's because, historically, a lot of the early aircraft designs use this layout.
Ah, okay.
In a conventional setup, the main gear wheels are positioned forward of the aircraft's center of gravity, which means you need a third support point at the back, usually a tail wheel, or sometimes on really early planes, just a simple skid.
A skid. That sounds rather basic, doesn't it?
It does sound simple now, yeah, but the chapter points out that skid could actually help slow the aircraft down after landing and give some directional stability too.
Huh.
Plus, the way the plane sits tilted up with conventional gear gave an interesting advantage back then.
Oh, yeah.
It allowed for a larger diameter propeller, which helped maximize thrust from those less powerful early engines.
More thrust definitely helps, and the chapter also mentions a benefit for unpaved runways.
Exactly. That higher ground clearance at the front, because the tail's low, is a real plus on rough, unprepared fields.
Makes sense.
And even today, some aircraft are still built with conventional gear, partly for that reason operating on rough terrain, and also because the tailwheel setup is generally lighter. Saves some weight.
And figure 13-to-4 shows a steerable one, right? On a pit special, so it's not just passive.
Nope. Provides directional control on the ground.
Interesting. Okay, moving on to something that sounds a bit less conventional: tandem landing gear. What's the idea behind that design?
Tandem gear, yeah. Figure 13-to-5 shows it well. It basically involves aligning the main gear wheels along the aircraft's center line front to back.
Along the fuselage.
Right. This setup is particularly useful in a couple of unique situations. The chapter mentions aircraft with really flexible wings, like sailplanes.
Ah. Yeah.
Spreading the load along the fuselage like that helps manage the stress on those lighter wing structures, allows for designs that might not work with wing-mounted gear.
Flexible wings.
Yeah.
Yeah, you don't see that on your typical airliner?
Not at all. The chapter also points to specific military aircraft like the B-52 bomber, which uses tandem gear.
Right, the BUFF.
And then there's the Harrier jump jet, the VTOL one. It also uses a tandem arrangement but adds small outrigger gear under the wings for stability during vertical flight.
Wow, yeah, you can see that in the figure. Those outriggers look essential for hovering.
Absolutely. It really shows how specialized gear can be tailored for very specific needs.
Okay, so finally, in the arrangement category, we have tricycle-type landing gear. The chapter says this is the most common arrangement today. What makes it so popular?
That's right. It really is the standard now. Tricycle gear, like in figure 13-to-6, has the two main gear assemblies under the wings or fuselage, and then a third steerable nose gear right at the front.
And a big advantage?
Stability, mainly, especially during takeoff and landing. Having that wheel out front greatly reduces the risk of the aircraft tipping onto its nose.
Yeah, that sounds like a pretty fundamental safety improvement.
It really is. And as the chapter details, tricycle gear involves a whole host of components. You got the shock struts, which we'll get into.
Right.
Steering systems, brakes, wheels, retraction mechanism, safety devices. Figure 1310 gives you a sense of the complexity just looking at one main gear leg on a big transport jet.
A lot going on there. Okay, so we've got the layouts.
Yeah.
Now let's talk about whether the gear stays down or gets tucked away. Fixed versus retractable. The chapter notes that small, slower aircraft often use fixed gear. Why not just make everything retractable for better efficiency?
That's a great question, and it comes back to that trade-off we mentioned. For smaller, slower planes, the weight and complexity of building a retraction system.
Right, all the actuators and doors.
Exactly. It can actually outweigh the aerodynamic benefit you'd get from reducing the drag.
So the drag isn't such a big deal at lower speeds?
Well, it's always there. But parasite drag, the drag from things sticking out into the airflow, increases dramatically with speed. So as the chapter explains, once you get to faster aircraft,
Like jets?
right, or even faster piston planes,
Yeah.
that drag from exposed landing gear becomes a really significant penalty.
So at some point, the performance gain from hiding the wheels becomes worth the extra weight and mechanics.
Precisely. For faster aircraft, retractable gear is pretty much essential to minimize that drag, get higher speeds, and better fuel efficiency.
Interestingly, the chapter also mentions pilots sometimes use the gear intentionally to slow down.
Yeah, extending the landing gear definitely increases drag, so it can be used like a speed brake in certain situations,
On E-Trick.
like a built-in air brake. So how does retraction actually work? Where does the gear go?
Retractable gear is designed to fold up neatly into compartments in the fuselage, or wings, those are the wheel wells.
Okay.
And to keep the airflow smooth when the gear is up, many systems use panels attached right to the gear struts that fit snugly into the openings. Figure 1312 shows that on a 737.
Ah, I see.
Other planes might have separate doors that open, let the gear swing in or out, and then close again to keep the aircraft surface really smooth.
Got it. Okay, that makes sense. Now, landing isn't exactly a gentle process. All that weight coming down needs to be managed somehow. Let's talk shock absorption.
Crucial stuff.
The chapter highlights two main ways landing gear control impact forces. What are they?
Okay, so the gear manages that landing impact in two key ways. First, it basically changes the rate at which that energy hits the airframe. It spreads the impact out over a bit more time, rather than one sudden jolt.
Softens the blow. Exactly. And second, it actually absorbs some of that energy by converting it into heat.
Turning downward force into heat, clever physics. The chapter mentions non-shock absorbing gear too, where early landings just incredibly rough.
You can only imagine. Yeah, the chapter says before they developed things like curved spring steel struts, a lot of early planes had rigid, welded steel gear.
Ouch.
With that kind of setup, yeah, the landing shock went pretty directly into the airframe. The pneumatic tires helped cushion things a bit, thankfully. Figure 1314 shows that kind of rigid gear.
Right.
And even today, things like helicopters with skids often have rigid gear because their landings are typically lower impact. Figure 1313 shows some examples.
So tires give some initial cushion, but for a really smooth landing, you need something more. That brings us to shock struts, especially air-oil struts. How do those work?
Right. Aerial struts or oleo struts are really the standards for modern aircraft. The basic idea is an inner cylinder, the piston, sliding inside an outer cylinder. The magic comes from how hydraulic fluid and compressed air or nitrogen interact inside those cylinders. Figure 1316 gives a good look inside.
So when the plane lands, the strut compresses. What's happening with the fluid and gas?
As the strut compresses, that lower cylinder, the piston, gets forced up into the upper cylinder. This pushes hydraulic fluid from the lower chamber up into the upper chamber through a small opening, an orifice.
Right.
Now, many struts use a tapered metering pin that moves through this orifice, like in Figure 1316. As the strut compresses further, the pin gets thicker where it passes through the orifice, restricting the flow more.
Ah, so the resistance changes.
Exactly. Forcing that fluid through the narrowing gap creates resistance, friction, basically, and that dissipates a lot of the impact energy as heat. Figure 1317 shows another way, using a metering tube to do the same thing.
So the fluid being squeezed absorbs the initial shock by turning motion into heat. What about the compressed air or nitrogen?
That acts like an air spring. As the fluid moves up, it compresses the air or nitrogen in the upper chamber even more. This compressed gas provides the final cushioning effect as the strut nears the end of its travel, preventing a hard bottoming out. Sort of a two-stage thing. Fluid handles the big hit, gas smooths out the end.
A very efficient energy management system. The chapter also mentions a damping or snubbing device. What's that for?
That handles the rebound. After the compression, the strut wants to spring back out, right?
Naturally.
But if it springs back too fast, you get a harsh jolt as it fully extends, which isn't good. The damping device, maybe a recoil valve or tube, restricts the fluid flow during extension too, slowing it down.
Controlling the rebound, like on a car suspension.
Exactly the same principle. Prevents damage and keeps things smooth.
Okay. The chapter then goes into other parts like the axle.
Yeah, usually the axle where the wheels mount is built right into the lower cylinder, as you see in figure 13-18. Sometimes it's a separate piece bolted on. And the upper cylinder, of course, has the attachments to mount the whole strut to the aircraft structure.
And what about the servicing valve and packing gland? They sound important for keeping it working.
Absolutely essential. The servicing valve is usually on the upper cylinder. That's where technicians add hydraulic fluid and charge the strut with air or nitrogen to the correct pressure.
Got it.
The packing gland creates the seal where the inner cylinder slides into the outer one, keeping the fluid and gas inside. And there's usually a wiper ring, too, to scrape off dirt and contaminants before they can reach the main seal and cause leaks.
Makes sense. Keep the dirt out.
Yeah, keeping that exposed piston rod clean helps the wiper do its job. Figure 13-23 shows the whole landing sequence: compression, fluid flow, air compression, and yeah, during taxi, the tires and struts work together to soak up the bumps.
So a complex system for a smooth ride. Now, once the wheels are down, they need to point the right way. Wheel alignment, toe in, toe out, camber. Why is this critical?
Proper alignment is key for a few things: stable ground handling, minimizing uneven tire wear, and preventing stress on the gear components. Toe in and toe out, shown in figure 13-28, is about whether the wheels point slightly inwards or outwards relative to the aircraft's center line. Ideally, they're parallel, but sometimes a slight angle is specified.
And how do they check that? Sounds precise.
It is. Figure 13-29 shows a common way. You use a straight edge across the tires and a carpenter's square reference to the plane's axis. You can see if the tire edges are parallel or angled in or out. It's quite hands-on.
Interesting. What about camber? That's the vertical tilt. Right?
Exactly. Camber, like in figure 13-30, is the tilt of the wheel top inwards or outwards. Positive camber means the top tilts out. Negative means it tilts in. You measure that with the bubble protractor against the wheel.
And if these are out of spec, how do they adjust them?
It depends on the gear type. On spring steel gear, common on smaller planes, you might add or remove papered shims where the axle bolts on.
Okay.
On airfoil struts, adjustments are often made using shims in the torque links, those scissor-like linkages you see, to tweak the toe angle. Figure 13-31 shows that.
Right, the torque links.
But the key thing, as the chapter stresses, is always follow the manufacturer's specific instructions for any adjustments. Precision is vital.
Absolutely. Okay, so all this gear needs solid attachment points. And if it retracts, it needs to pivot smoothly. Landing gear support and retraction. Where does it attach?
It attaches to the really strong parts of the airframe: wing spars, reinforced fuselage members, places designed to take those big landing loads.
Makes sense.
For retractable gear, the attachments have to be strong and allow for that pivoting movement into the wheel wells.
And how does that pivoting usually happen? The chapter mentions a trunnion.
Yeah, the trunnion is a common design. Figure 13-32 shows it. It's basically a fixed pivot point, part of the upper strut, with bearings that allow the whole gear leg to swing. It lets the gear move from vertical for landing to horizontal when stowed.
Ah, the pivot point itself.
Right. And often there's a drag strut, maybe hinged, like in figure 13-33, that holds it rigidly in place when down, but folds up during retraction.
Clever geometry.
Yeah.
So what actually makes the gear move up and down?
On smaller planes, it can be surprisingly simple. Maybe a lever in the cockpit connected through mechanical linkages. Pull the lever, gear moves.
Manual power.
Sometimes with chains, sprockets, even a hand crank to give the pilot some mechanical advantage.
A hand crank. Wow. What about bigger planes? Hydraulics, I assume.
Oh, yeah. Larger aircraft almost always use hydraulic systems. Figure 13-37 gives a simplified look. Hydraulic fluid under pressure pushes actuators, basically hydraulic rams, to move the gear.
Okay.
And if there are gear doors, their movement has to be perfectly timed with the gear. This can be done with mechanical links or separate hydraulic actuators for the doors.
Timing is everything.
Exactly. That's where sequence valves come in, like A, B, C, and D in that diagram. They ensure things happen in the right order, like the gear is fully clear before the doors start to close.
A carefully choreographed dance. But what if the main hydraulics fail? Is there a backup?
Absolutely. Safety is critical. All retractable gear planes have emergency extension systems.
Okay, like what?
On some smaller planes, there might be an emergency handle that just releases the uplocks, the latches, holding the gear up.
Yeah.
Gravity then does the work, the gear free falls down.
Gravity assist?
Figures 1335 and 1336 show a free fall valve that bypasses the hydraulics to let gravity take over.
Makes sense. What about bigger aircraft?
Larger planes often have multiple redundant hydraulic systems anyway, so a complete failure affecting the gear is less likely.
Good redundancy.
But even then, there's usually a manual or secondary way to release those uplocks for a gravity fall. Figure 1338 shows manual release handles in a 737 cockpit.
Okay.
And some planes, maybe where gravity isn't enough, might have a fully manual hand crank system as a backup. The details are always in the maintenance manual, of course.
Right. Crucial documentation. So backups are key. Let's talk more about safety devices, ground locks, and gear indicators.
Ground locks are physical safety devices, like pins you insert, shown in figure 1342, that mechanically prevent the gear from retracting or collapsing when the plane's on the ground for maintenance or parking. Absolutely vital.
A physical lock.
Yep. Gear indicators, on the other hand, are for the pilots in flight. Usually lights on the panel, like in figures 1343 and 1344.
Green for down, usually.
Typically, yeah. Different lights show if each gear is up, down, and locked, or maybe still in transit. Some systems even show the door status. It's crucial information for the crew.
Quick visual confirmation, essential. The chapter also mentions nose wheel centering. Why is that needed?
Because most nose wheels steer, right?
Uh-huh.
You need to make sure that nose wheel is pointing straight ahead before it retracts into the wheel well. If it's turned, it could jam or get damaged going up.
Ah, okay. How does it center?
Often using centering cams built into the strut mechanism, like in figure 1345. When the strut extends fully with weight off, these cams engage and align the wheel. Smaller planes might use a simpler guide pin on the strut that runs into a track in the well to straighten it as it retracts.
Clever mechanical solutions. All these details add up to reliable operation. Now, keeping it all working needs regular checks. Landing gear inspection, what are the key things?
Inspections are critical. Visually checking everything for cleanliness, corrosion, any physical damage, struts, linkages, structures.
That's basics.
Absolutely. Then you've got detailed checks of wheel bearings, tires, brakes. We'll get more into those specifics later. Verifying the gear position indicators, warning lights, horns are all working.
Testing the warnings.
And confirming the ground safety locks are okay and used correctly. That's fundamental.
So a really thorough visual and functional check. What else?
You also check the emergency systems, make sure handles are in the right place, inspect the wheels themselves for cracks or corrosion, check the tie bolts are tight. If there's an anti-skid system, check its wiring. We talked about tires wear, cuts, pressure, slippage marks. Lubrication is key too, all the moving parts. Steering mechanisms. Figure 1346 shows proper bearing lubrication, making sure grease gets right in there.
It's a meticulous process, covering big structures down to lubrication details.
Yeah.
Sometimes inspection isn't enough, adjustments are needed. Landing gear rigging, an adjustment, when does that happen?
Yeah, adjustments to switches, doors, linkages, latches, locks might be needed periodically to keep everything within tolerance. Maybe after replacing parts like actuators, or just due to normal wear.
Okay.
When you replace or adjust actuators, you have to check for over-travel, that little bit of extra movement beyond just fully extending or retracting. That extra bit is often what triggers the locking mechanisms.
The final push that locks it. What are some specific adjustments technicians make?
The chapter gives examples, but stresses that procedures vary a lot between aircraft. Adjusting latches is kind of the things that hold the gear up or down or hold the doors open or closed.
Right.
Figures 1347 and 48 show checking roller clearance on a door latch, making sure it engages properly. It involves careful measurements of clearances, rollers, bushings. Figure 1349 even shows adjusting a door hinge for alignment.
Precision adjustments. What about drag and side brace adjustments?
Each gear usually has adjustments to ensure it locks down properly. A common way is a side brace that snaps over center, like in figure 1350. You adjust a locking link to make sure it goes fully over center, physically preventing collapse.
That over-center lock is key?
Definitely. You do this with a plane on jacks. And you might check the downlock spring tension, too, with a spring scale to make sure it meets spec and keeps the lock engaged.
And after any adjustments, you'd test it, right?
Absolutely. Retraction tests or swinging the gear are essential after maintenance, adjustments, sometimes even after a hard landing, or just for regular checks. The manual details exactly what to look for during these tests.
Makes sense. Verify everything works correctly. Okay, let's shift to moving on the ground. Nose wheel steering. How does that usually work?
Most planes, except maybe some very small ones using differential braking, have steerable nose wheels controlled from the cockpit.
Right.
Figure 1353 shows a basic hydraulic system. Usually, cockpit controls, often linked to rudder pedals, send input to a hydraulic control valve.
A metering valve.
Exactly. It directs hydraulic fluid to actuators that rotate the lower part of the nose strut, steering the wheel.
Hydraulics again. What about the accumulator and relief valve mentioned?
Those help maintain steady pressure in the system. This gives immediate steering response, but also allows the steering cylinders to act as shimmy dampers.
Shimmy dampers like shock absorbers for steering. To stop wobbles.
Precisely. Essential for smooth taxiing and preventing damage from oscillations. Figures 1321 and 1355 show shimmy dampers.
Got it.
The chapter also describes a follow-up mechanism. Once you reach the desired turn angle, this mechanism automatically returns the control valve to neutral, so the wheel stops turning.
Prevents oversteering.
Right. And often, rudder pedal input is used for small steering inputs at higher speeds, like during the takeoff or landing roll. Safety valves are also there to relieve pressure if hydraulics fail, letting the nose wheel caster freely. Figure 1354 shows a more detailed system diagram for a larger plane.
So a sophisticated system for precise ground control. Now the wheels themselves, critical components. What are modern wheels made of?
Modern wheels are typically two-piece, split designs bolted together. Usually cast or forged from strong, but light aluminum or magnesium alloy. Figure 1359 shows this.
And they're tubeless mostly.
Yeah, there's an O-ring seal between the halves to make them airtight for tubeless tires.
The chapter emphasizes the bead seat area. Why is that so crucial?
The bead seat is where the tire seals against the wheel rim. It takes huge tensile loads from the inflated tire, especially during landing impacts, so it's often specially rolled during manufacturing to make it stronger.
Reinforcing that critical contact point. The chapter also says the two halves aren't identical.
Right. The main difference, shown in figure 1361, is the inboard half has features to connect to the brake rotors.
The brakes mount inboard.
Usually. This might be keyways that match tangs on the brake rotor or separate steel keys bolted to the wheel. Smaller planes might bolt the rotor directly. That's the key difference, brake mounting.
Okay, clear. What about bearing cavities and thermal plugs?
Both halves have machined cavities for the tapered roller bearings and grease seals. Thermal plugs, though, are a safety feature on high-performance wheels, usually on the inner half. See figure 1362.
What do they do?
During really heavy braking, wheels can get incredibly hot, risking a tire explosion. These plugs have a core made of metal that melts at a specific, relatively low temperature.
A fusible plug.
Exactly. If the wheel gets too hot, the core melts, letting the tire deflate safely before it blows. Critical safety device. If one melts, the tire is done, and the wheel needs a thorough heat damage inspection.
An ingenious failsafe. And the anti-skid sensor, where does that usually mount?
Typically on the outboard wheel half, as shown in figure 1360. It monitors the wheel's rotation speed for the anti-skid system.
Okay, so wheels are complex, engineered parts. Maintaining them requires care. Inspection, removal, disassembly, cleaning, where does that start?
Often starts with the wheel still on the plane. Visual checks for obvious damage. Making sure all the tie bolts holding the halves together are present and tight. A missing bolt is a big deal. Check the dust cap, anti-skid sensor are secure. Check the inboard side where it meets the brake. No chafing, keys are secure.
Basic checks can catch big problems. What about actually removing a wheel? Safety precautions.
Huge emphasis on safety here. The chapter warns strongly. Always deflate the tire completely before removing the wheel, especially high-pressure tires.
Why is that?
If there's hidden damage, like broken tie bolts, the air pressure alone might be holding a damaged reel together. Removing the axle nut could cause it to explode. Very dangerous.
Wow, okay. Deflate first.
Always. Also, let tires cool down for hours after landing before touching them. Heat increases pressure. Approach from front or rear, not the side. Don't stand in line with the valve core when deflating. And usually, only remove one wheel from a pair at a time for stability if the plane's on jacks.
Vital safety rules? Once it's off, how do you get the tire off the rim? They can get stuck, right?
They can get really seated. You need specialized bead breakers, mechanical or hydraulic presses shown in figure 1364 to push the tire bead away from the rim flange.
Use the right tool.
Absolutely. And make sure there's zero air pressure left. And crucially, never pry the tire off with screwdrivers or levers. Aircraft wheels are soft alloys. Nicking them can create stress points leading to failure.
Got it. Specialized press, no prying. Once the tire's off, disassembling the wheel itself.
Do it in a clean area. Remove the bearings carefully first, then remove the tie bolts holding the halves together. The chapter advises against using impact wrenches on these bolts.
Why no impact wrench?
The hammering action can damage the soft wheel alloys, maybe distort the bolt holes or the wheel halves. Use hand tools.
Makes sense. Avoid damage. And cleaning the wheel halves.
Use a manufacturer-recommended solvent and a soft brush. No abrasives, scrapers, or harsh pads that can damage the protective coating on the wheel. If that coating's compromised, corrosion starts fast. Then dry thoroughly, maybe with compressed air.
Okay, clean wheels are ready for inspection. Bearings are obviously critical. Inspecting and lubricating them, what damage signs?
You look closely for several things. False Brinelling often looks like rusty stains in the grease. Staining or surface marks grayish-black streaks, maybe from water. Edging or corrosion, reddish-brown discoloration, pitting, and bruising indented surfaces on rollers or races. Figures 1369 to 72 show examples.
Subtle signs are important. What about the bearing cup in the wheel? Does it come out?
Usually not for routine inspection, but you must check it's seated firmly, not loose or rotating in the wheel half. Figure 1373 shows that. If it does need replacing, it involves carefully heating the wheel in an oven to expand it, then pressing or tapping the cup out using non-metallic drifts. It's a precise process needing the manufacturer's instructions.
And careful handling and the right grease are essential.
Absolutely paramount. Keep bearings clean, dry, away from vibration, even in storage. Use only the manufacturer-recommended lubricant. And pressure packing tools, like in Figure 1374, are best to force out old grease and ensure the new grease fills everything.
Okay, clean, properly greased bearings are key. What about inspecting the wheel halves, tie bolts, fusible plugs?
Visually inspect every surface of the wheel halves for damage specified by the maker, plus non-destructive testing. Eddy current is often used for cracks in the bead seat area, Figure 1375.
Finding hidden cracks.
Exactly. Dye penetrant might be used for cracks in the brake drive key area, Figure 1376. The tie bolts themselves need checking, often with magnetic particle inspection for fatigue cracks. They take a lot of load.
Right.
Check the brake. Drive keys are secure, no wear or corrosion. And visually inspect the fusible plugs, Figure 1377. Make sure the cores haven't melted or deformed, which indicates overheating. If one looks bad, replace them all on that wheel.
A multi-pronged inspection. What about wheel balancing?
Wheel sets are statically balanced at the factory with small weights bolted on, like in Figure 1378. These are permanent parts.
Okay.
When you mount a new tire, the whole assembly might need additional balancing. This is done with supplemental weights added around the rim. They fine-tune the balance with the specific tire.
Got it. Balance is important for smooth running. Now let's switch to stopping power. Brakes. The chapter lists several types. What are they?
Yeah, quite a variety depending on the aircraft. Floating disc, fixed disc, dual disc, multiple disc, or segmented rotor, and expander tube brakes.
Let's start with floating disc brakes. How do they work?
Okay, floating disc, figures 1379, 1380, you have a caliper straddling the disc. Pistons with brake pads, or pucks, are on the outboard side. Stationary pads are inboard. The disc itself is keyed to the wheel, so it rotates, but it can also slide sideways a little bit in those keys, hence floating.
The disc floats.
Right. When you apply pressure, the outboard pistons push their pucks against the disc. This pushes the whole disc slightly sideways until the inboard pads also make contact. It helps even out the pressure on both sides.
Clever.
Figure 1381 shows return springs pull the pads back, and self-adjusting pins maintain the right clearance as the pads wear.
Okay, so how do fixed disc brakes differ?
In fixed disc brakes, figures 1382, 1383, the disc is bolted rigidly to the wheel. It doesn't float.
So what moves?
The caliper assembly itself, with the linings, can float laterally. It slides on anchor bolts within bushings in the torque plate, which is fixed to the axle. When pressure hits the pistons, the whole caliper assembly slides to center itself on the fixed disc, again aiming for even pressure.
Okay, so the caliper floats instead of the disc. What about dual disc brakes?
Just like it sounds, figure 1384. Two discs keyed to the wheel. Used when one disc isn't enough stopping power, heavier or faster planes. There's a center carrier between the discs with linings on both sides, squeezing both discs at once.
More surface area for more stopping power. Makes sense. Multiple disc brakes sound even more complex.
They are. Figures 1385 to 87 show the setup. You have a stack of alternating rotors and stators. Rotors are keyed to the wheel and spin with it. Stators are fixed to the brake housing or torque tube.
Like a clutch pack.
Exactly like that. Hydraulic pressure squeezes this whole stack together. Rotors against stators generating a huge amount of friction between all those surfaces. Very powerful braking. They also have automatic adjusters for wear.
Used on larger aircraft, I assume.
Yes, typically on transport category aircraft where high braking energy needs to be dissipated.
The chapter also mentions carbon brakes and expander tube brakes briefly.
Right. Carbon brakes, figure 1390, are the high-tech option, mainly for jets. Much lighter than steel, handle heat way better, last longer, Main downside is cost.
Lighter and better performance, but pricey.
Yep. Expander tube brakes, figures 13, 91, 92, are a different, often older design, sometimes on lighter planes. Lightweight, low pressure. It's basically a reinforced rubber tube inside a drum. Pressure expands the tube, pushing brake blocks against the drum. Simple and effective for certain applications.
A real range of technologies. How are these actually activated? Different actuating systems.
Yes, several ways. From simple direct systems to complex power systems using the main aircraft hydraulics.
Let's start simple. Independent master cylinders. Where are those used?
Mostly on small, light planes that don't have a central hydraulic system. Like in Figure 1393, each main wheel brake has its own master cylinder connected mechanically to a rudder pedal.
Like car brakes, basically.
Very similar principle. Pilot pushes pedal, master cylinder creates pressure just for that brake line. They have reservoirs, Figure 1394, and compensating ports, Figures 1395-96, for fluid expansion. Bleeding out air is critical, Figure 13-119. Parking brakes are often just mechanical latches holding the pedals down.
Self-contained system for each brake. What about boosted brakes?
Boosted systems, Figure 1397, are for planes needing more stopping power than the pilot can easily apply directly, but maybe not needing full power brakes.
So hydraulic help.
Exactly. It uses the aircraft's main hydraulic system pressure to augment the pilot's pedal force during heavy braking. The master cylinders have extra valves to bring in that hydraulic boost when needed.
Okay, amplifying the pilot's effort. Then there are full power brake systems for the big jets.
Correct. Power brakes, Figure 1398, are standard on large, high-performance aircraft. They use the main aircraft hydraulic system as a power source.
No direct master cylinders then?
Nope. Instead, brake control valves, or metering valves, Figure 1399, 13100, connected to the pedals, regulate the flow of high-pressure hydraulic fluid from the main system to the brakes.
More sophisticated control.
Much more. They often have features like graduated pressure control, artificial pedal feel units, Figure 13101, for feedback, redundancy, anti-skid integration, hydraulic fuses, shuttle valves for multiple power sources. Very complex systems.
Lot going on there. What about emergency brakes if the main hydraulics fail completely?
Vital backup. Often uses hydraulic accumulators precharged with nitrogen, Figure 13102. These store pressurized fluid.
A reserve tank of pressure.
Basically, yes. A separate control lever or valve in the cockpit, Figure 13103, releases this stored pressure directly to the brakes. Sometimes a shutoff valve traps the pressure in the brakes, too.
A self-contained backup. The chapter also mentions brake deboosters. What's their job?
Deboosters, Figure 13104, are used when the brake assemblies themselves aren't designed for the full pressure of the main hydraulic system. The debooster reduces the system pressure down to what the brakes can handle.
A pressure reducer.
Right. Some, called lockout deboosters, also act like hydraulic fuses if there's a big leak downstream. They shut off flow to that brake to prevent losing all system fluid.
Another safety feature. Now, with all this stopping power, wheels can lock up. Anti-skid systems, how do they work?
Anti-skid, Figures 13-109 to 112, is crucial on jets with power brakes. It detects when a wheel is about to lock up or is actually skidding, and automatically releases brake pressure just to that wheel, momentarily, allowing it to spin up again and regain traction. Prevents flat-spotting tires and maintains steering control during braking.
Sounds like a fast feedback loop. How does it do that?
Components. Key components. Real speed sensors on each axle constantly measure rotation speed. This goes to an anti-skid control unit.
The brain of the system.
Right. It converts the speed signal, calculates the deceleration rate for each wheel, and compares it to an ideal braking reference. If a wheel decelerates too fast, imminent skid.
It steps in.
Exactly. It sends a signal to a control valve for that wheel's brake. This valve quickly reduces hydraulic pressure to that brake. Wheel speeds up, regains grip. Then the control unit allows pressure to be reapplied, but modulates it to keep just below the skid point. It's constantly adjusting pressure to each wheel individually.
Very sophisticated real-time control. Keeping these systems working requires regular checks on aircraft brake service.
Yes, routine checks are vital. Always follow the manufacturer's manual. Common things. Check brake lining wear. Check for air in the system. Spongy pedals are a sign. Check fluid levels and type. Inspect lines for leaks. Check bolt torques.
How do you check lining wear on the aircraft?
Several ways. Many brakes have wear indicator pins, Figure 13114, 1389. As pads wear, the pin's exposed length changes. You measure it against limits in the manual.
A physical indicator.
Yes. Others might require direct measurement of the pad thickness, Figure 13116. On multiple disc brakes, you might measure the gap between the pressure plate and housing when brakes are applied, figure 13.117. Always check the manual for the specific method.
And if there is air in the system, you mentioned bleeding.
Right. Bleeding removes trapped air. Can be done top-down using gravity or bottom-up using pressure, figure 13.119. Fluid is pushed through, forcing air out of bleed ports. Need to bleed main, auxiliary, and emergency systems if applicable. Essential for a firm pedal feel and proper function.
Got it. What about off-aircraft service, when the brake assembly is removed?
That allows much deeper inspection. Check all bolts, threads, inspect discs for wear, cracks, warping. Check pads linings for wear, unevenness, secure attachment. Check automatic adjuster pins aren't bent or binding. Inspect the torque tube for wear, cracks, often using NDT, like magnetic particle. Examine the housing, pistons for damage, wear limits, corrosion. Always replace seals during overhaul, checking part numbers and shelf life. Figure 13.125 shows realigning brake shoes with rivets needs care, and often a burn-in procedure for new linings is required.
A full overhaul process. Brakes can malfunction, though. Overheating, dragging brakes.
Overheating is serious. Can distort parts, weaken metal. Look for discoloration, bluish tint on steel, burning smell. After a high-energy event like a rejected takeoff or signs of overheat, brakes must be removed and inspected for heat damage, cracks, warping. Replace seals, too.
Okay.
Dragging brakes. That's when linings don't fully retract. Causes constant friction, wear, overheating. Could be weak return springs, binding pins, warped discs, or even air in the lines. Using the wrong parts can also cause it. Needs fixing promptly.
And chattering or squealing.
Often means uneven contact between linings and disc drum. Could be a warped disc, misalignment in the stack on multi-disc brakes. Overheated discs can develop hotspots that cause this too. The vibration isn't just annoying, it can damage things, so investigate it.
Right, noises mean something's wrong. Okay, final point of contact. Tires. Lots of detail here. Types, construction, inspection, maintenance. Let's start with the different types.
Okay, several types designed for different needs. Type I is old, fixed gear. Type 3, figure 13.126, is common for general aviation, lower speeds, lower pressure, wider profile. Type 7, figure 13.127, is for jets, high performance, high pressure, narrower profile. Type 8, figure 13.128, is for very high performance jets, very high pressure, heavy loads, low profile. Plus other designators related to rim width ratios.
A specific tire for each job. What about ply rating? Does it mean the actual number of plies?
Not anymore, really. It used to. Now, with modern materials, ply rating is more an index of the tire's strength and load capacity, regardless of the actual number of layers. Higher rating means stronger tire.
Okay, a strength index. Bias ply versus radial. Are radials common now?
Bias ply figure 13.129 has been the traditional aircraft tire construction plies run at an angle. Gives good sidewall flexibility for landing impacts.
Right.
Radials, figure 13.130, where plies run 90 degrees to rotation, are newer in aviation. Very strong tread area, carry high loads well. They're being used more, but bias ply is still very common due to its landing characteristics.
Both have their place. Let's look inside a tire. Key construction parts.
Figure 13.131 shows a cross-section. The bead is the strong wire bundle at the inner edge that grips the wheel rim. Critical anchor point.
Got it.
Sidewall protects the carcass, plies the main fabric layers, giving strength. Breakers are extra layers under the tread for strength and puncture resistance. Tread is the outer layer for contact, wear, grip, heat dissipation, often grooved for cooling and water channeling. Inner liner seals the air in tubeless tires. Small vent holes in the sidewall let trapped air escape from between plies. And some nose tires have a deflector rib to keep water spray out of engines.
A complex structure. Tire inspection is crucial, too. What to look for on the aircraft.
Number 1, correct inflation pressure. Check it under load with a calibrated gauge, figure 13.134, referencing the manual. Account for temperature changes.
Under or overinflation is bad.
Very bad. Underinflation causes heat buildup, uneven wear, risk of slipping on the rim, sidewall damage. Overinflation reduces grip, wears the center tread faster, makes it more prone to impact damage. Correct pressure is fundamental.
Okay, pressure is king. What else?
Tread condition. Look for even wear. Uneven wear suggests alignment or pressure issues. Check wear limits, how much tread is left before reinforcing plies show. Figures 13.136, 13.137.
Wear limits are key.
Absolutely. Also inspect the tread surface carefully for damage. Cuts exposing plies, undercutting, peeled ribs, figure 13.140. Flat spots from skids, figure 13.141. Bulges separations, figure 13.142. Chevron cuts, chipping, cracking, figure 13.145. Any significant damage means removal.
Lots of potential damage types. What about the sidewall?
Check for exposed cords, crack and checking, figure 13.147. Bulges, Could mean internal separation very bad. Also, check for contamination from oil or hydraulic fluid, which degrades rubber.
Thorough visual check. What about safe handling, especially if damaged or overheated?
Treat damaged or overheated, inflated tires as potentially explosive. Figure 13148. Don't approach immediately after a high-energy event. Let it cool. Approach from an angle, not head-on.
Caution is key.
Always deflate completely before removal, using proper tools, standing aside. Mark damaged areas before deflation. Use proper bead breakers. Figure 13150-151. No prying. Only soapy water for lube. Never hydrocarbons.
Strict safety rules. What about inspecting tires off the aircraft?
Can do a more detailed check then. Focus on the bead area for damage. Inspect closely after any overheating. Probe cuts to check depth. Look for bulges. Differentiate between ply separation, reject, and tread separation, maybe retreadable. Check sidewall cords. Consider if it's suitable for retreading by an approved facility.
Retreading is an option for some. How about storing tires?
Proper storage prevents degradation. Avoid long-term horizontal stacking. Figure 13152 distorts lower tires. Ideal is cool, dry, dark, well-ventilated, clean.
Keep them out of the elements.
And away from ozone sources, lights, motors, and hydrocarbon chemicals, fuel, solvents. Temperature range usually 0-40 degrees C, 321-4 degrees air.
Stable environment is best. What about tubes? Still used sometimes.
Yes, mainly older, or some GA planes, made of natural rubber. Store them carefully, ideally in original carton. Avoid creases. Keep away from ozone light. Inspect for leaks. Water immersion test before installing. Check inside a tire for anything sharp first. Figure 13153 shows a good tube.
Similar care needed. Mounting tires, tubeless, and tube type.
Critical job needs a licensed tech following manufacturer instructions. Final tire inspection first. Use correct lube, non-hydrocarbon on aluminum, never on magnesium, or mount dry if specified.
Orientation matters.
Yes, align balance marks, red dot on tire to valve stem or light spot on wheel. Tighten tie bolts in sequence to correct torque. Initial inflation must be in a safety cage from a distance.
Safety cage is essential.
Absolutely. Let it sit 12 hours after inflation for stretching seating, then recheck adjust pressure. Use talc for tube types, inflate tube types partially, deflate fully, then inflate again, wait 12 hours, final check. It's a process.
Precise and safety-focused. Tire balancing again static and dynamic.
Static balancing is done at the factory. Dynamic balancing, figure 13159, is an option some maintenance shops offer. Not always mandatory, but a well-balanced assembly runs smoother, reduces shimmy, potentially less wear elsewhere. Figure 13160 shows balance weights.
Okay, finally, operational tips for tire life and safety.
Maintain correct inflation, number 1. Proper taxiing, avoid obstacles, stay on pavement, moderate speed, minimize hard braking, gentle large radius turns, avoid scrubbing tires and pivots.
Pilot technique matters.
Huge difference. Pre-flight tire inspection, always. Be aware of runway conditions. Figure 13162. Smooth landings minimize impact. Understand common failure causes. Foreign objects, figure 13161. Flat spots, overheating from heavy braking, rejected takeoff. Awareness helps maximize tire life and safety.
Wow, we've really covered a lot of ground there, from the basic structure to the intricacies of brakes and tires. It's truly remarkable how complex these landing gear systems are.
Absolutely. They're absolutely critical for safety, and even things that seem simple, like wheels and tires, involve some incredibly sophisticated engineering and really meticulous maintenance.
Yeah, you definitely see that. And the sheer number of safety features and procedures built into every part, the retraction, the braking, anti-skid, the tires themselves, it's all designed for reliability.
It certainly gives you a much deeper appreciation the next time you watch a plane land, doesn't it? Thinking about all those systems working together seamlessly.
It really does. Makes you wonder, though, with materials, science, and tech always advancing, what might landing gear look like in the future? More integrated systems, new materials, completely different concepts, maybe.
That's a great question. Lighter, stronger, smarter systems seem likely. Maybe even more electric actuation. It's definitely a fascinating area to watch.